So today I'll be just running through the work I did for my dissertation, for my master's here, that's working on trying to reduce the two qubit count for circuit optimization using the ZX calculus. And I have about 20 slides, 10 to 20 slides. It'll be mostly high level, and then we can talk about things afterwards. Okay, so the main problem is that circuit optimization in the ZX calculus typically results in a high number of two qubit gates compared to other like off-the-shelf circuit optimization techniques. And typically this is a consequence of having to extract a circuit from a ZX diagram. So you can simplify a ZX diagram, to fixed point, but when you have to extract a circuit, the process typically results in a lot of CNOT gates. More specifically, this manifests in physics. This manifests in two methods. The first is teleport reduce, which only affects the T count. So you don't get any optimization in the original number of CNOTs or two qubit gates. And then full reduce, it can actually increase the number of two qubit gates by virtue of its necessity for extraction. And based on this, as I mentioned, is this underlying assumption that simplifying a ZX diagram corresponds to simplifying the circuit that will be obtained via extraction from that diagram. And this is generally true, but there's an additional sort of truth that we can take advantage of for optimization that isn't currently being exploited, which is that local variants of a ZX diagram, so ones that the graph complexity may be similar, can induce circuits with surprisingly different complexities. So given a ZX diagram, you can change it locally in different ways that don't necessarily reduce the number of edges or reduce the number of spiders, but they can actually yield circuits with significant differences in complexity. Okay, so how are we going to take advantage of this, or how did we take advantage of this? So we want to search this space of local variants for an equivalent ZX diagram, which is more amenable to extraction. And this requires a couple of things. To do this requires a couple of things. First is what we call congruences. And these are just rules in the ZX calculus that are non-simplification rules. So rules that will just produce equivalent diagrams that you can still, from which you can still extract a circuit, but sort of help us search this space. The second is a search procedure. So given rules to generate this space, we need ways of actually searching the space because it's exponential, or it's combinatorial. And then we also need an objective function to guide search. So for congruences, we just extend the notions of local complementation and pivoting that are used in previous optimization techniques in physics. And without going too much into detail, I have them here for completeness, but we basically define two congruences that apply for arbitrary phases in connectivity based on both local complementation and pivoting. And these are the rules that we're going to use to sort of generate the space of equivalent ZX diagrams. Okay, then we need search procedures or optimization techniques to search this space. So we use simulated annealing and genetic algorithms. And for those not familiar, simulated annealing is an optimization technique that mimics annealing in metallurgy, which is the controlled cooling of a material in order for it to reach its most stable form. So say you have a molten hot metal. You cool it in a very controlled fashion in a way that for the purpose of obtaining a stable form of that molten hot metal as it cools. And the analogy for optimization in computing is you slowly decrease the probability of accepting worse solutions. So as you maintain a single state, and as you're searching the solution, as you're searching the space, you start with a very high probability of accepting a worse solution as you apply actions that give you variance or equivalent variance of that state. And then as search progresses, you become a bit more stringent and say, okay, I'm only going to accept a solution if it's truly better than the current state. And this is modulated by a temperature parameter and a cooling parameter, which determine this probability of accepting a worse solution and the rate at which this probability decreases. Then the second procedure that we use, the second search procedure that we use is genetic algorithms. Similarly, a pretty simple search procedure, mimics Darwinian evolution rather than annealing. And again, very intuitive. So you maintain a population of states rather than a single state as in annealing. And it requires, as with Darwinian evolution, it requires the notions of fitness and mutation operators to create diversity. So first, you spawn sort of your initial population, and this population we call the mutants. Given such an initial population, we conduct a series of generations, and each generation consists of the following. First, we evaluate the fitness of all the mutants. Then we apply some selection procedure to select the next the population that will proceed to the next generation. And then we apply some mutation and crossover operators that will determine that introduce diversity for the population in the next generation. And for our purposes, we use something called tournament selection, and the mutation operators in our case will be these congruences. Happy to talk more about tournament selection if anybody's interested. And then at the end, you just return the mutant with the best fitness throughout all of search across all the generations. So these are the two search procedures we use. Lastly, both of these search procedures require an objective function to guide search, like what is a good ZX diagram. And that is determined by the circuit complexity of the complexity of the circuit that can be extracted from that diagram. So first we define just an explicit quantitative measure of circuit complexity, and that's 10 times the number of 2 qubit gates plus the number of single qubit gates. And this 10 scaling factor is an artifact of 2 qubit gates generally being like in order of magnitude more costly to implement. Cost in terms of like the noise they introduce in the circuit. In addition to this, and this is like a well-defined measure of circuit complexity, but the issue is that every time you want to measure a diagram, you have to extract the circuit from it, which is costly. So we're also interested to see if there are other measures of a diagram that can serve as proxies for the complexity of the circuit. And examples of such are the number of edges, the density of the graph, the centrality of the graph. So we experiment with these things as well. Okay, so given this set of congruences, these search procedures, and this objective function, this is sort of a big overview of our strategy in general. So first, we take an input circuit, and then the first thing we want to do is just simplify its ZX diagram using off-the-shelf methods. We just want to simplify as much as we can, mainly to reduce the T count. And those familiar with physics will know that there are two main routes of getting there. One is via teleport reduce, which again only reduces the T count and doesn't affect the 2 qubit gate, the number of 2 qubit gates, and then apply some circuit level optimizations. The other is just to apply full reduce, which is sort of this more master method of applying local complementation pivot. So we take this simplified ZX diagram that corresponds to the input circuit, and then we apply either one of these search procedures over the space generated by these congruences to try to find, guided by the optimization function or functions defined in the previous slide, to try to find an equivalent diagram whose circuit that you obtain via extraction is less complex. After search, we take that circuit, we apply full reduce because we're going to have to extract anyway. We extract, apply circuit level optimizations, and then we have our optimized circuit. So that's the strategy. Now I'm going to talk about results, and this is the pipeline used. Okay, so now an overview of results. The first thing we did is just refine the above strategy, and there are a couple opportunities for refinement. And by refine, I mean sort of tweak that strategy before looking at overall performance. We only want to look at overall performance when sort of all the parameters are tuned. So what's the first refinement we can make? The objective function. Do we have to extract every single time? This refinement really only matters with respect to execution time. But yeah, the main question is, do any of these measures of a ZX diagram serve as reliable proxies for this measure of circuit complexity that we've defined? So we generated 500 random circuits with different numbers of qubits and depths, and measured the correlation coefficient. And the answer is no. You need to extract the circuit and measure it. Maybe there's some other measures on the ZX diagram that we didn't think about or didn't test, but this is the case so far. Okay, what's another refinement we can make? So what about the probability of applying either one of the congruences? Is one better than the other? Do we want to apply one more than the other? Do we want to apply only one but not the other? So again, we generated a bunch of random circuits with different depths, and we tried, for all of these refinements, we just use annealing because it's faster and the behavior likely generalizes to other optimization techniques. And the summary here was that if you're just doing if you're just including one of the congruences, local complementation far outperforms pivoting. And that's probably a consequence of the fact that one pivot is equivalent to 3 local complementations. So this search space is more coarse-grained than this search space. You can see my mouse, right? Okay, yeah. However, best performance on average is generally obtained by including both, and it doesn't seem to matter too much in what proportion. So by default, we just 50-50 select the congruences with a 50-50 percentage probability. Okay, so once you've chosen, throughout search, once you've chosen the congruence that you want to apply, should we just sample subjects to apply that congruence uniformly, or should we weight them in particular ways? And again, without going into, there are various things you could try. For example, you may want to pivot on the spider with the highest degree, or with the spider whose the sum of the degrees of its neighbors is highest, because maybe that will change the connectivity in such a way that will that has a better chance of reducing circuit complexity. And we tried a bunch of these things, and I can go into more detail if people are interested, but the final answer was sort of no, we didn't have any weightings for subjects of these congruences that really increase performance. So again, we sort of just go with uniform sampling. Okay, then you sort of get into like search procedure specific parameters, like how many iterations do we run for annealing? So generated a bunch of random circuits, annealed over them, and plotted the probability of future improvement beyond a certain number of steps. And there's some interpretation issues here because, you know, if you've capped out your number of iterations at 5,000, there's going to be a lower likelihood of seeing improvement at 4,000 than 2,000, just because there's only 1,000 rather than 3,000 more iterations to go. But in general, we see that improvement in annealing sort of tapers around this 2,500 mark. So that's where we fixed our number of iterations. We did a similar thing for the evolutionary approach, using different population sizes and generation numbers and numbers of generations. And a couple things were interesting. First of all, that the population size didn't really matter that much. You see here that the same complexities, the same reductions in circuit complexity were obtained for different population sizes. This sort of lack of a difference is also reflected in this likelihood of improvement throughout the search, which is interesting. So we settled at a population size of 20 and roughly 40 generations, which we push a bit more later. Okay, so after these refinements, we wanted to test our method, and so there's just 2 more slides on this, and then future work. So for the initial results, we generated 10 circuits for varying numbers of qubits, and then applied each optimization procedure over those circuits and just averaged the reduction we got from the original input circuit. So let me just run through some abbreviations here. TR, FR correspond to just the off-the-shelf physics methods, teleport, reduce, flow reduce, plus the additional circuit level optimizations. TR seed, FR seed indicate the initial method of obtaining that simplified ZX diagram to seed search. And we see a couple things here. First of all, the most obvious is that our method, which is this chunk here, these 4, works well, outperforms off-the-shelf methods in physics for low numbers of qubits, particularly with annealing. Annealing outperforms this genetic approach. So that's promising. We can get, on the order of 60% improvement for circuits with 4 qubits. Oh, and I should have mentioned, this is all these circuits have 15 gates per qubit. So for example, for circuits for 10 random circuits with 4 qubits and 60 gates, we can get about a 60% reduction in circuit complexity, which outperforms teleport, reduce, and flow reduce, which is promising. But then as we increase the number of qubits, this ability to reduce the complexity decreases. And eventually, as is the problem with full reduce, we start getting a circuit that's worse than the input circuit. So there's some scaling issues, and this is likely a consequence of limits in the extraction procedure. But yeah. the last thing is there aren't any noticeable differences in how you obtain this initial simplified diagram that you to seed search. So going forward, we just sort of fix one method. We just use this teleport reduce method. Okay, so after that, we wanted to check a couple more things. The first was, okay, can we push this approach more? So to do that, we did 3 random restarts for annealing, and we increased the number of generations for the genetic approach. So 75 generations and 3 random restarts for annealing, and just pick the best one when optimizing a given circuit. We also wanted to test against IBM's approach and CQC's approach. So we took the off-the-shelf methods from Qiskit and Ticket. And lastly, we also wanted to test on how it did with circuits with more gates. So rather than just doing the 15 gates per qubit, we also tested it on 10 random circuits per qubit with 40 gates per qubit. And you start getting into some scaling issues, like it does start to take long. And it's actually still running, like it's still running for these numbers of qubits. But in general, you can see the trend. So in general, we see that you do get more performance for when there's more gates per qubit, you get a higher, there's more opportunity for reduction in complexity. For example, on the 6 qubit circuits, we get about 50% reduction versus 35% reduction with annealing when there's more gates per qubit. We also see that increasing the number of generations in the evolutionary approach doesn't really offer that much performance advantage. Similar with the random restarts, like with annealing, doing it 3 times doesn't get you that much better performance than just doing it once. And lastly, we see, so on the previous slide, we saw that our approach outperforms at least the off-the-shelf physics methods for low numbers of qubits. And we also see that it outperforms sort of IBM's and CQC's approach for low numbers of qubits as well, which is cool. Especially take this case, for example. So neither physics, in the 6 qubit case, neither physics method was outperforming CQC or IBM's approach, but with this search over these local variants, you actually see a big reduction, which is cool. And we see it also in this, when you increase the number of gates per qubit, we get, again, in the 6 qubit case, we get a 50% reduction over, IBM or CQC's 13 or 15% reduction. So there's promise here, and the limiting factor appears to be extraction, or maybe some other congruences that help explore the search space. Okay, so a couple things for future work and conclusions. This approach works for small numbers of qubits. Extraction is likely the bottleneck, and it does scale well with depth. So when you increase the number of gates, there's more opportunity for reduction, as is the case with other optimization techniques, but it allows this technique to shine a bit more. I didn't show times, but this approach is significantly more computationally expensive. But if you just care about optimizing the circuit, time shouldn't be a major concern. Optimizing in a minute or a minute and a half instead of half a second, if this is a circuit you want to run, isn't the end of the world. There's some testing to do on benchmark circuits. I have to do a bit of legwork in finding what the previous best numbers of 2 qubit gates were there. And the last thing that might be interesting to try in future work is that simplifying a ZX diagram to fixed point, just simplifying it as much as you can, may not be the best approach. Maybe it induces some extra complexity upon extraction. So I'm curious to see what would happen if you sort of stop the simplification of a ZX diagram halfway, and then search local variants from there, or to start from the beginning and include these congruences in some action set that you can search over. So these are things I'm curious about. This is it. This is it. Only other thing I want to mention is that all reductions you see here, or that I showed, are a consequence of a reduction in the number of 2 qubit gates. So I don't show numbers for this, but none of these reductions, in all these cases of optimization, the number of single qubit gates never decreases. It's always the number of 2 qubit gates, and that's the space that's being searched. So thanks, and now happy to take questions.
Thanks, Ryan. Any questions?
I have many, but maybe someone else can go first, because I can just keep talking.
Anybody want to ask something before John's deluge of questions? Neil, go ahead.
Maybe just an opening question. So you say that you've got about 15 gates per qubit, which means that the nature or the depth, I guess you could say, of these circuits is changing substantially as you increase the number of qubits. So you're looking at circuits that look as though they would have different depths. Or
Yes.
I was wondering if you thought that this might be one of the main features that might be giving rise to differences in performance of these optimization techniques for circuits with different numbers of qubits, or whether there are indications that there are other things at play as well.
I agree. I don't think this is a particularly principled approach to compare the performance across numbers of qubits. Definitely open to better ways of fixing that, and I generally agree with you there.
I have a related question. Is there a plot of how it scales with depth, gate depth, or was it only 1540 tried?
Only 1540 tried, but that is something I should do.
Okay, so there's no way to know the scaling given that's just 2 data points.
Yep.
I guess it'll also be quite sensitive to what relative ratios of gates you decide to use. So, for instance, something like the T count, I expect would affect this quite a bit if these are random circuits.
Yep.
Can I ask more about the generation of the random benchmarking circuits, like the relative ratios and how many non-Clifford phases and how many multi-qubit gates versus single?
To generate the random circuits, I just used the function in physics that generates random circuits with C0, Hadamard, and phase gates. I just use the default probabilities. I forget what they are. I can check if you're curious. But I am interested to see how it performs on circuits with a different structure. For example, some of these benchmark circuits that have been reported in previous papers, which I should have those results over the next couple of days. I'm curious to see how it works on different forms of circuits. But in terms of specific numbers for these random circuits, I just use the default parameters in physics for generating random circuits with these gate types.
That's good. John and I have code on UCC, so unitary coupled cluster onsets from Calton and Will's paper from TCAT.
Okay, great. Thank you.
Yeah, so let me start with some questions. So first question, let me first make a remark about the 40 gates per qubit, 50 gates per qubit. I think a more natural metric would be to do a number of gates per square of qubit, because if you think about a Clifford circuit, then the normal form has a quadratic number of gates per qubit in terms of qubits. So I think you would get a more random sampling if you increase the number of gates per at least the square per qubit, and like maybe even more, because the complexity of a circuit can increase like a whole lot if you increase the number of qubits. So that's just a remark. The question I had is, can you say a bit more about the genetic algorithm approach? Because I can understand how you would do simulate annealing, because then you just try different rewrites. But how would you mutate between populations while preserving symmetry?
Yeah, sure. So take the input simplified CX diagram that you're going to use as seed search. Now say you're gonna do the genetic approach with a population of, say, like 20 mutants, and you're going to run it for 50 generations. So the first thing you do is you create 20 identical copies of that ZX diagram that you want to search over. And you could introduce initial mutations if you want. That's sort of a stylistic or implementation detail. So you get your initial population. That's just the 20 ZX diagrams. And then at each generation, the fitness evaluation is clear. You just you extract the circuit and measure its complexity. The mutation operators are just applying these congruences. So you just randomly select a congruence, randomly select a subject to apply that congruence for each mutant you do this. And then in that manner, you get diversity for the next generation upon which you measure fitness, select, proceed. Does that make sense? And then the optimization is in the selection approach, is in the selection technique.
Okay, but that's mutation. How do you do crossover?
Oh, okay, yeah. So so we don't do any crossover, and this is an opportunity for this could be explored in future work, but it's actually fairly common in genetic, like in the literature of genetic algorithms, it's fairly common to not see a lot of crossover. Like oftentimes the first thing people try is no crossover.
Okay, so essentially there's no direct integration between the different.
No, exactly.
Yeah. Okay.
But so some things that I didn't show here is that the search space doesn't seem that complex, and by that I mean it seems as though the best solution is being found, which is why I'm hesitant to try more complex things like crossover or graph neural networks or other things. Like I think in general, the best or close to the best optimization that you can do with these congruences is being found. That's why I think the bottlenecks are extraction or the actual action set that you use for search.
Yeah, I think it also is not very clear what crossover would even be in this context. I
agree.
Okay, so other question. You had this slide about the maximum number of iterations you need for simulated annealing. I can imagine that this number needs to be different if you have a bigger circuit, right?
Yeah. So I should say, so I presented this a bit backwards with the expectation of that question. So I first identified that sort of this approach works well for, at most 12 qubits. And then I went back and sort of optimized the number of iterations. So again, not shown here, the circuits that I tested this on were like 4 to 14 qubits. And in the dissertation, I say this is generalized, etc. But yeah, I totally agree.
Okay, yeah, that makes sense.
And when you say you throw this procedure at a circuit with 20 qubits and you run it for 100,000 iterations, which I've done, and different temperatures and cooling parameters, it doesn't work.
Yeah, I at some point also tried like simulate annealing on Clifford normal forms to try to minimize the number of gates, and there I found a similar effect where it worked really well for a small number of qubits, but as the number of qubits became larger, the effect like diminished quite quickly.
What was your intuition for why that was?
Yeah, I don't really know. Maybe just because the number of possibilities just increases so rapidly that you're just exploring a very small part of the space. Like I don't know.
And for that reason, I expected genetic algorithms to do better for larger qubits, which they don't necessarily, which has surprised me. Because my expectation was the exact same.
Can I throw in a suspicion? I think the reason why simulated annealing might do better than genetic algorithms is because I think that the cost function is more well behaved for a lower number of qubits, whereas for a larger search space, you might get stuck in too many local minimums. And so if your cost, like for example, just if you're optimizing a circuit by hand, you might sometimes have to make the circuit more complex in order to get to the optimal form after.
So why would that? So I would think that genetic algorithms would be good for that because they maintain this very diverse population. You're not just maintaining a single state. So even if it's one of these cases where you have to sort of search for a more complex circuit or enter a more complex space, I wouldn't. Could you repeat again why, or flesh out? I think annealing would be better for that.
Annealing is more than, say, like more convex optimizations. It would be less likely to get stuck in a local minimum versus kind of classical, more optimization methods will inherently be more likely. But if you do increase diversity of your population enough in genetic algorithms, you can.
Yeah, exactly. That's why I was surprised at the population size. Like even if that was the case at low numbers of populations, I would expect if you jack up the population size to 100, it would start to eke out of those local minima better than annealing did, which I haven't seen. But it's an interesting point.
That's where I'm confused or not sure about. I wanted to ask, where is the cutoff per se for how brutally you initiate selection on your genetic algorithms?
What do you mean initiate selection?
Like that selection function, how much do you kill off of your population?
Okay, great point. So good. Yeah. So so the selection method I use isn't thresholded. So I use a selection method called tournament selection, and basically what that does is, say you have a population of 40, right? You want to obtain a new population of 40. You conduct 40 tournaments, and so to get this new population, 40 times, you do this 40 times, you pick two mutants from the current population, and then you have them compete. You just pick the one with the better fitness, and they move along. So there's actually a possibility that the best one in your current population won't get moved along. But the point is it's not thresholded. It's you conduct a series of tournaments. Does that make sense?
Yeah, it does. So I guess then the convexity is bounded by the tournament selection. In that sense, is something that is more fit. A series of optimizations that is more fit might not necessarily happen if you terminate that mutation before it, like if it gets selected out before it's optimal.
The one benefit of the selection method is that it allows you, it's a bit better for searching like optimization paths in which you have to explore suboptimal variants. Does that answer your question? Like say you threshold, you're going to lose out on all the mutants that may have a bit higher complexity, but then will actually reduce the complexity. Tournament selection is part of the reason tournament selection is good, is because it prevents that, or it allows for that to happen, whichever way you see it.
What do you mean when you say take two mutants and let them compete? Is that just comparing their scores?
Yeah. Sorry, I'm being like, I'm drawing out the analogy.
So then I was kind of confused how you said that the most fit might not make it.
Oh yeah, because you sample with replacement. So you have your population of 40 mutants. You want to get a new population of 40 mutants. To do so, you just conduct 40 tournaments. So in each tournament, you just pick two guys, pick two mutants from the population, have them compete, put the winner in the next basket, and then you do it again. Okay. So there's a chance that you never sample the best one. For what it's worth, I've tried this with where you always guarantee, like on this problem, I've tried where you guarantee that the next one makes it along and it doesn't improve performance. So I don't think it's an issue.
I see. Okay. But so the difference between this and doing a threshold-based technique is this does allow weaker mutants.
Yeah. The person who founded like genetic algorithms really advocates this approach. He's I forget his name. Some old University of Michigan. Right. Tom Holland, I think.
Would it does it make a difference if instead you kick out the loser rather than taking the winner, so that you would definitely remove the weakest ones rather than not necessarily keeping the strongest?
Maybe. I think it's an alternative, but it's also not super clear how you do that. Like, okay, you kick out the mutants, but then how do you, like, what is a loser? How do you add back in? How do you maintain the size, the population size? Like, who takes their place? I think it's an interesting thought. It's not clear to me why it would necessarily be better or how exactly it would work.
I think then if there was a winner, then you would definitely have that in your winning set because it would never lose if picked, versus you might not just by chance never pick the winner.
Oh, sure. And that's why I mentioned I did some experiments where you do ensure that the winner is kept around, like tournament selection plus the winner, plus the overall winner. And it didn't improve performance, so it doesn't seem to be an issue necessarily.
So Will Simmons has a question in the chat. I assume this is because he doesn't want to, or he can't speak. But
It'd be interesting to see.
yeah, he says it would be interesting to see if the performance can be replicated by localizing this effect. E.g., at some point in extraction, search the space of congruences over a small graph. There's a drilling in the background, he says. Search the space of congruences over a small subgraph close to the frontier, just trying to minimize the cost of extracting that subgraph. And repeat this as you continue. So can we do this piecewise over subgraphs and prevent the exponential scaling, essentially?
For what it's worth, I completely agree. This is something that we've talked about, and I just forgot to mention it here. But I totally agree. Like, I think that would be a fun, interesting, promising thing to try. Just haven't gotten around to it.
So something that occurred to me kind of along this vein while you were talking, and this is also related to this idea of maybe we shouldn't fully simplify stuff. If you only apply spider fusion and an identity, then the graph that comes out is actually a graph that has flow rather than G-flow. A consequence of this is you never have to do any Gaussian elimination to extract a node. The only thing you have to do is just keep pulling CZs off of the frontier, and it'll always free up a node, and then you can sort of keep going. And a consequence of this is that the 2-qubit gates that come out of your extraction are always less than or equal to the gates that go in. Because the Gaussian elimination is the only thing that increases the 2-qubit gate count, I think. So potentially something you could do is use those graphs to seed the annealer.
Yeah, that's true.
And then, you know, so now you do start doing some local complementation and stuff. So you do maybe increase the 2-qubit gate count, but you're starting at a point where you're no worse off than you started off. I mean, so sometimes we're starting off with circuits which have massively bad C0 counts, and we're trying to even get back to where we started. So potentially starting the annealer from here could perform fairly well.
Yeah, I agree. Is that extraction like implemented anywhere?
I think if you, well, actually it is. You can find it. I think it might be called basic extract or something, but I can find it. It's the one that appears in the practicals. So these Jupyter notebooks that came with the course.
I think if you just apply the circuit extract function on a graph of that shape, it does basically the same thing.
Yeah, that's also true.
I think
the only difference really is that you shouldn't apply full simplify first. You should just apply the sort of spider simplification stuff, and then hope this doesn't break the extractor. I think the extractor makes some assumptions about the form of this graph that's coming in, but we've talked about that before, I think.
Yeah, you can just first convert everything to Z spiders and then fuse all the stuff, cancel all the Hadamard, and you get something with the right.
Yeah, I actually ended up making. I have a couple of utilities for like putting something in graph-like form that I'll probably fork and push to business.
Yeah, so I think if you want to do this, then you should have some rewrite rules that like the ones that you have, where you get a new kind of vertex, but then also have rules where you just apply the standard pivot simplification, standard localization that you can remove stuff, and then you sort of decide, do I remove stuff or add stuff like that? Yeah, that might be a good idea too.
Is that is what you're describing? Is that sort of this master search approach that I've described, where you just lump these congruences in with a big master action set with a bunch of simplifications and conduct a search?
Yeah. So what you described is not going to this fixed point, but starting from what Alex described.
Yeah.
But then also allowing these actual simplification steps as steps in your simulated annealing.
Right, and then I think the search base. The second you sort of add those with this more benign starting point, I think that's when maybe you could get a lot of benefit from the genetic approach. Like, I think maybe, population size 100, 200 starts to become beneficial. Yeah, just a guess.
Can I ask some other questions?
Uh-huh.
So I know that Alex has experimented with this kind of simulated annealing stuff before. Can you say how what you did is different? Like, of course, you did the genetic algorithm, which, as far as I know, Alex did not do.
Oh yeah. I mean, there were a couple. First of all, like, I found a couple bugs in the anneal. Like, I think the results from previous annealing approaches were like not representative. Like, I think there were bugs, so they weren't representative of the benefit you get from annealing. I tried and then I tried pivoting, and I tried the genetic approach. I sort of just, beyond trying pivoting and beyond trying the genetic approach, I'm not sure there's too much novelty in what I tried from what Alex had started with.
Yeah, so I think you started with my code, right? And then and then you fixed it and then implemented a bunch of other stuff.
Another question. I was kind of surprised to see that your ticket implementation, or like the simplification used from ticket, that sometimes increased gate count. So now I'm wondering which ticket method.
Yeah, I was surprised. So this is something I was thinking about yesterday. I use their full peephole method, which is the one that they advertise as their sort of catch-all. But it is my sense that they sort of provide a mixed bag of techniques, and if you have advice on ones that better represent ticket's abilities, that would be helpful. For Qiskit, I think it's clear. I just use their like transpiler with the highest optimization level.
Mm-hmm.
Yeah, I don't even trust the results from Qiskit, because as far as I know, they are renowned for not preserving semantics of circuits.
I actually don't trust the one. I mean, if I were to not trust one, it would be ticket, because I've been checking the quality after optimization and it doesn't hold. And I had some conversation on a GitHub issue that I was somewhat unsatisfied with. So I think there are question marks on some of these techniques. There are question marks on the like soundness. Something to keep in mind.
And also, like, looking at these numbers, I might have a different interpretation for why the method does worse on larger numbers of qubits. Looking at the Qiskit and ticket, like, they don't improve the method much either, and the teleport reduce doesn't do either. So, like, it looks to me that your circuit is so sparse or so random that it's basically optimal already. And then the reason that the methods with physics are doing worse is because we're sort of scrambling the circuit, and we're going away from this optimality because we're forgetting structure. We're getting this reduced graph. And then we're trying to find it again, but through like infinite annealing. So it's very hard to get back to optimal nature. Mm-hmm. While in the lower number of qubits, since you have so many gates per qubit, you are bound to be like in a super random, not optimized state. So then there's much more space for finding something more optimal.
Yep.
So I think this might be an effect of the fact that your higher number of qubit circuits are too sparse, maybe. which is like why I suggested like having the number of gates with the quadratic number of qubits that you have.
Yeah, could you re-explain that again? I have that starred in my notes, but
yeah. So like looking at all the sort of gate-based methods, they all like don't perform, like they don't do much, like they do a few percent difference.
oh sure.
That to me seems to say that it's already quite optimal, at least a sort of like a local gate level.
Sorry, what you just described makes sense, but why quadratic in the number of qubit? Like why number of gates?
Yeah, that's sort of the intuition I have from Clifford's. Like maybe quadratic is not even enough. Maybe it needs to be to the third power or fourth power. I don't know. But sort of like just thinking about like each qubit can connect to every other qubit via a C0. So just think about the number of types of connections as a quadratic amount. So like if you want to be able to have a C0 between every pair of qubits in each layer, you want to have a quadratic number. But that's my intuition there.
Yep.
So
like you might even think instead of generating the random circuits you do now, is that you generate a random Clifford, then put T gates in a layer in a random way, and then do another random Clifford. And then you just repeat that a fixed number of times. Like that maybe gives you a better distribution of random circuits.
I think you can test the density by using quantum volume as a metric.
Oh, okay, that's okay.
Yeah, I guess as a sort of first degree approximation of what John said, if you think about a random Clifford unitary, that will have quadratically many gates in it. So I mean, in that sense, maybe that makes more sense as a starting point. And even say a random C0 circuit, you know, we'll tend to have quadratically many C0s in it. So somehow, as you grow, if you keep putting linearly many gates, it just gets to the point to where, you know, it's becoming very unlikely that any particular pair of qubits becomes connected by a 2-qubit gate.
I'd also be interested in seeing the results because, of course, you wanna test benchmark circuits, which that's definitely important. But also just different classes of random circuits. Like if you have a random Toffoli circuit, I think the behavior could be very different.
Did you run any of this on the benchmark circuits, Ryan?
No, I actually want to ask you because I've been to find like what the current best number of 2-qubit gates for there. Like in the previous T-count paper for all the benchmarks, you guys compiled like what the best T-count was for all the benchmarks, but I wanted to ask you the best way to find the best known number of 2-qubit gates for them.
Okay. Well, maybe John wants to stick around also to give some advice on that.
Sorry, what was that a question for me?
This doesn't include everybody else. Alex and I were gonna stick around afterwards to just chat quickly about the benchmark circuits and how you guys just compiled like the current best for each circuit, because I want to do the same for the 2-qubit count rather than the T count. So he suggests that you might want to stick around for that conversation as well.
Oh yeah. I think there's Jupiter open.
Okay, great.
Are there any other questions? Okay. Well, thanks, Ryan. I'll clap.
Yeah. Thanks everybody for coming.